All right. So it wouldn't be a Tockey podcast without having beer in the studio. So you remember what I told you when we first started brewing together? When you taught me how to brew, my biggest fear
was, I don't remember.
My biggest fear was basically poisoning somebody.
Oh, you can't do that.
Making something like botulism or whatnot, right? The only thing I could do is make crappy beer, right?
Yeah. You can never hurt anybody.
Can you hear the pour here? Look at that. Listen to that. Isn't that awesome? Bing. You like that, huh? All right. Well, hello again. This is Mark Griffin, Director of Customer Solutions here at Construx, a team of software engineering experts led by legendary author Steve McConnell. Here we believe every software team can be more successful at delivering higher values of business value. In every episode of Inspect and Adapt, we talk with one of our consultants and explore a recent engagement. We describe the issues we were faced with and how we solved them, and we have a little fun along the way. So let's get to it. Today we welcome longtime Construx principal consultant and my good friend Steve Tockey into the studio. This guy's resume is a mile long, but just to mention some aspects of his career, he's worked as a programmer, an analyst, a designer, and a researcher for organizations that include Lawrence Livermore National Laboratory, the Boeing Company, and Collins Aerospace. He has a master's in software engineering from Seattle University, where he has been an adjunct professor, and a BA in computer science from Cal Berkeley.
Berkeley, of course.
Berkeley, of course. He's a CSDP and chaired the certification committee for the IEEE Computer Society. He's written 2 books, Return on Software, and a just recently released How to Engineer Software. At Construx, Steve travels the world applying his deep and broad software knowledge to help engineers in organizations increase their performance. He taught me how to homebrew beer, and together we brewed the beer that Construx serves at its private classes here in Seattle. So welcome, my friend.
Thank you. Good to see you, Mark.
So today the subject is a recent course that you taught here in Seattle, a revised version of your design patterns class. And we have kind of 3 topics to explore, so I think we're going to jump right into the first one and see where we go from there. And so there's a particular issue that you covered in the class that talked about complexity as a fundamental design principle, and in more particular, balancing local and global complexity in that environment. So let's maybe define some terms here. What do you mean by local and global complexity?
Well, before we actually dive into that, it's probably a good idea to say, why do we even care about the topic?
Okay.
I have a list of the top 5 reasons that software projects get into trouble, but it will be too much of a distraction to talk about them now. But the bottom line is that the number 1 reason that software projects get into trouble that is directly in control of the software people. There are other reasons that are bigger, but they're out of the control of the software people directly. The biggest thing that the software people have direct control over is the complexity in the code base.
Okay.
And I should mention that where this data is coming from, partly it's coming from industry data, various reports that get published, but mostly it's when I'm going out and working with organizations. A very common question is, what causes you trouble on your software projects? And we just make a list. And what I've got is about 20 years worth of data, and I thought it would be interesting to go back and kind of summarize that data. And so what we're talking about here is the summarization of about 20 years of working with real organizations, and not me saying, I think this is your problem, them telling me this is our problem.
So data-driven here.
Very data-driven.
Okay.
And so it ends up being the most significant issue that is within your control on the software team.
Okay.
And in fact, Steve McConnell has said before that the prime directive of a software professional is to manage complexity. Now, the whole root problem turns out to be, in my opinion, that it's okay to say we need to control complexity, but if we don't have a way of measuring the complexity, we don't really have a way of managing the complexity. And so there's been some limited amount of research on the whole idea of how do we even measure the complexity in software. The oldest of the known measures is something called cyclomatic complexity. And what it's doing is essentially counting the number of decisions that are inside of some function. It's best if you do it at a function level. But some studies have shown a correlation to, as the cyclomatic complexity of the function increases, the density of the defects in that function increases with it. If you look at cyclomatic complexity 1 through 5, which is basically 4 or fewer decisions in the function, versus functions that have a cyclomatic complexity of 15 or greater, that the expectation or the defect density is more than 13.4 times greater in a function with a cyclomatic complexity of 15 or greater. And
so that's an interesting thing. I know that we do technology due diligence audits here at Construx. Our CTO does work in that area, and one of the metrics he uses is that cyclomatic complexity statistic. And part of the reason I think he shows that is that it's an indication to someone who is potentially acquiring that company. If that complexity level gets too high, then there's a concern about the supportability, maintainability of whatever code they are acquiring.
Exactly. You have a much higher probability that defects are in that section of code. Look, the bottom line is that defects are not uniformly distributed throughout the code base. They're definitely not uniformly distributed. They cluster around complexity.
Okay.
And so if you know where the complexity is, you know where your defect trouble spots are. It's actually rather simple. And so cyclomatic complexity turns out to be one of the measures. Another very important measure is called depth of decision nesting. Now, what's going on here, cyclomatic complexity just counts raw decisions. How many decisions do you have? What depth of decision nesting does is look at decisions inside of decisions inside of decisions. And some studies have shown that it's one thing to have decisions, but another thing when the decisions are deeply nested within other decisions, that you have now a dependency between the decisions, and that drives up the probability of defects. Because again, defects cluster around complexity, and this is just a measure of where the complexity is.
Okay. So you have this notion, you introduced this notion in the class as part of discussing fundamental design principles, this notion of trying to minimize overall complexity. So you have local complexity and global complexity. Can you give me some examples of either of those? I mean, local, I think, would be cyclomatic complexity, be one of them, right?
Right, and depth of decision nesting is also an example of local complexity. What I mean when I say local complexity, it's complexity that's contained within a single function.
A single function, okay.
Whereas global complexity is not telling me about complexity of the function itself, it's telling me about the complexity of how the function fits into its larger environment. And there are two recognized examples there. One of the examples is called fan out. If I am a function, what is the number of other functions that I call, other functions that I am aware of? I am function A. Well, I call functions X, Y, and Z. That means my fan out is 3.
Okay.
So that's one element of global complexity. And another element of global complexity, there's some interesting research coming out of the Netherlands, Amsterdam to be exact, that's showing that the number of parameters that you have on a function, if you have too many parameters, it will also drive up the number of defects. And so how does this function fit into its environment with how many parameters does it require and how many other functions does it call are, again, environmental, global views of complexity.
Gotcha.
Now, the whole issue here is that if you have a function that is too locally complex, you can refactor it. You can take some subset of the code that's in that function, shuffle it off to another function, thereby reducing the amount of decisions, the cyclomatic complexity, potentially depth of decision nesting, in the original function, but at the cost of increasing fan out. And so I'm trading.
So there's a trade-off.
Yeah, I'm trading local complexity for global complexity. And so the whole point here is that it varies in any one situation. I may see a small decrease in local complexity and get a big increase in global complexity. But the opposite could happen. I could have a big decrease in local complexity and a small increase in global complexity. It's not a linear trade-off all the way across. And so then the point is that if I can take advantage of the trade-offs of having big reductions in one of those kinds of complexities for small increases in the other kinds of complexities, then there has to be some kind of balance point, if not a point, at least a balance area,
right,
where it minimizes the overall complexity in the code base. And that's really the whole point of that principle, is to be trying to drive towards that balance point where I don't have too much local complexity and I don't have too much global complexity, but I have an appropriate balancing between both of them, which then minimizes the overall complexity of the whole code base.
So given your experience over the years, was it surprising to you that people in this class thought that this was an interesting subject, that they maybe weren't particularly aware of it, or how it tracks to project successes at all?
Right. In spite of the fact Cyclomatic Complexity actually being published in 1972 by a guy named Tom McCabe, it's been around. At least some people in the industry have known it for quite a long time. But when I'm working with groups, I'll sometimes just take a poll. Hey, how many of you have even heard of cyclomatic complexity before? And maybe I get a yes out of 10% of the people.
Wow, that's surprising.
It is amazingly surprising how low the knowledge of these things are. And so that's really the whole battle here. I don't think anybody really likes complexity in the code base, but unless you have more than a qualitative way of dealing with it, Lord Kelvin apparently is on record of having said, if you can't measure it, you can't manage it. And this is exactly the phenomenon in most organizations. Maybe they don't know they should manage complexity. Maybe they do know they should manage complexity, but they don't know how to manage complexity because they can't get a handle on it because they can't measure it.
But there are tools to help with that, right?
Well, that could
to some extent?
That could be a discussion in a whole different podcast. Yes, there are tools that report on a lot of metrics about code, the so-called static analysis tools. Mm-hmm. The key issue that I have with them is that most, I'll say 90% of what they're reporting on is not correlated with anything you really care about in the code. I mean, it's easy to measure things about the code. The real serious question is, does that measure actually matter?
Right.
And so what's missing is a correlation analysis that says you should pay attention to this measure. Don't really bother with that one. I mean, because we can come up with contrived measures. It's really easy to come up with contrived measures. It would, in fact, be possible to measure the average shoe size of the developers on the project team. We can do that. But does shoe size have anything to do with anybody's ability to write code or the quality of the code that gets written? The answer is absolutely not. And so most of the things that get reported, these static analysis tools tend to report on an amazing number of things on the assumption that if I report more things, you're more impressed, so you'll buy my tool than their tool.
Gotcha. Okay.
But the term that you would be very familiar with is the signal-to-noise ratio in this space is abysmal.
Yeah.
And so while I can get easily 20 or 30 numbers to pop out of a static analysis, only 4 are really worth paying attention to now.
Is that something that on a company-by-company basis they would determine what things out of a static analysis tool are relevant for their kinds of projects? Or is it something that an engineer would have to find out on their own in using these tools?
I think maybe eventually it might get to the point where certain measures are more important in certain spaces, but we're at a level of primitiveness in this space that everything that measures that matters to everybody. The number of decisions, the depth of decision nesting, the number of parameters, etc. And in fact, just to give a real example, I've actually seen code. Some programmer, got paid a lot of money to write a function that had 58 parameters.
Wow.
And how can you keep 58 parameters straight in the signature of the function on the first hand? And how is somebody who's going to call the function going to make sure that they understand 58 individual named parameters going into the did I get them in the right order? No wonder we have defects.
Right, and the poor engineer that inherits that code over time is going to have a lot of fun trying to figure out what's going on with it. Right?
If it can be figured out at all in the first place.
So structural complexity is important, and that's really a big thing that came out of that class. People recognized the notion of balancing that complexity as a fundamental design principle.
It's important, and you can measure it, and you can manage it, and now I've given you a tool that you can apply in your everyday code that allows you to make better code.
Well said. So why don't we dive a little deeper on a more holistic aspect of the class that you just recently taught. This is a design patterns class, and you introduce fundamental design principles when you teach the patterns class. In other words, the importance of understanding those principles when using patterns. And just for reference, the principles that you're calling out in this class are minimizing overall complexity, using abstraction, encapsulate design decisions, which effectively design by contract leads from that, maximizing cohesion, minimizing coupling, design by invariance. Is it Liskov? Is that how you say it? Liskov
substitutability principle.
Correct. And then favoring association over inheritance. I mean, that list obviously begs for another podcast, and I will definitely invite you back to go into the design list a little bit more. But for this particular environment, we really are talking about diving deeper into the patterns aspect of that. So you bring those up. Why bring up the principles in a design patterns class? What's the rationale for doing that?
Well, there's actually a number of reasons, some ulterior motives and some more surface motives. Some people are already familiar with what are known as the solid principles, originally developed by Robert Martin, Uncle Bob Martin. And so it's an acronym, SOLID, S, single responsibility, O, open, closed, et cetera, et cetera. So some people are familiar with those. And the point that I want to start off with is that I don't have any problem with the solid principles per se, other than they just don't go far enough. They're too small in scope that you need a broader set of principles that apply across a broader spectrum of the software. And solid, you're not going to go wrong by paying attention to solid. How do I rephrase this carefully? If you follow solid, universally there will be an advantage to following solid, but it will only carry you so far. This is a set of fundamental design principles that have been worked on for a large part of my 42-year career that are more broadly and more generally applicable than solid. It causes you to pay attention to things that you would not necessarily have paid attention to when you were just applying solid. And so part of this is just making people aware that there really are a set of fundamental principles that should guide us in how we build software. And it's sad that the amount of software that I see when I am looking at real code, this real code is just absolutely oblivious to these fundamental principles.
Okay, so when you explore like a particular pattern in the class, what's the mechanism for trying to get people to be aware of how there's something in a fundamental principle that's carried by that particular pattern? Right,
and so again, ulterior motives, less ulterior motives. In my experience, if you just take the patterns as face value, yeah, they're interesting, they're useful, they can solve interesting problems, et cetera, et cetera. But I don't think you really get a gut level understanding of what a pattern is really up to unless you understand why the pattern looks the way it does. And so that's the point of these fundamental design principles. All of these patterns are in some way either primarily driven by a fundamental design principle, or they're influenced in some significant way by one of these principles. Why does the pattern look the way it does? Well, here, let me tell you that, for example, strategy pattern looks the way it does mostly because encapsulation. It is encapsulating different ways of solving the same kind of problem. Now, it's influenced by Liskov substitutability and cohesion and coupling, but the primary driver here is to encapsulate different ways of solving a problem. And adapter pattern, for example, is going to be driven by a different set of primary drivers. And it's actually, to me, quite interesting to really get to understand what adapter pattern is up to, and then go take a look at proxy pattern and see what it's up to, and compare and contrast them at the principle level rather than just, oh, here's an interesting pattern and oh, here's another interesting pattern.
Right.
What makes
does it help
them
to
so
reinforce?
what makes them so interesting with respect to each other is because they kind of do opposite things in an interesting way that we'll probably talk about later.
Yeah, well, that's a good segue into another topic, in a particular topic in the class. And another thing that you indicated that they really seemed to jump all over was this idea of using design by contract as a principle, which is really about encapsulation, correct?
Encapsulation is the fundamental principle. Design by contract is how you make it happen in code.
Oh, I got you. Okay.
And so one is the end that I'm after, the other one is the means to the end. Design by contract is the means to the end.
I got you. Well, so why don't you give me, in layman's terms, kind of some examples, since the origins of this are really kind of in business contracting, right?
Not really.
Respects.
I mean, you may look at the terms as coming out of business contracting,
right?
Because a business contract, I want to buy a car, I want to buy a house, I want to get a kitchen remodeled. There are legal contracts involved, and the nature of those legal contracts is exactly the same nature as the contract that I have on a function in software.
Okay.
There's the what one party is responsible for doing, and then there is the what the other party is responsible for doing in exchange for what the first party is responsible. If I give you this amount of money, then you give me the car. If I give you this amount of money, you give me the house. If you remodel my kitchen to the standards that are appropriate, then I will give you this amount of money. If I, then you, but one key element in understanding contracts is if you don't, then I don't gotta. If you don't give the dealership the money, they're not going to give you the car.
Right.
Same with the house. You hired somebody on a contract to remodel your kitchen. They use substandard material. They didn't follow the plan, et cetera, et cetera. You're not legally obliged to pay them what you said. You can argue to either not pay them at all.
So that's in the contract per se,
right?
So how does that? Yeah, so give me a simple example of that in a software sense. How does that? How would you set something up in a contract sense like that?
So if I have a function that has some number of parameters, let's just say that one of the parameters might be a pointer to something, okay? And there's a deeper issue here that we'll probably have to bring up in a moment, but just at this introductory level, I have a function, it has a parameter, the type of the parameter is a pointer type. Well, it's very different in terms of, is it safe to call this function with the pointer being null? Can you call me safely with a null pointer? Or if you call me with a null pointer, when I dereference the pointer inside the function, boom, we'll get a null pointer exception. And so this is the key to understanding encapsulation designed by contract, that if you are a programmer who wants to use some function that takes a pointer type variable as input, and all I showed you was the signature of the function, here's this function, call it whatever you want, and it has 3 parameters. The second parameter is a pointer to a something. Is it safe to call the function with a null pointer? The only way you are going to be able to answer that is to go into the code, read the code, and see what happens if you give it a null pointer. And the whole point of encapsulation was to keep you from going
Having
in
to do that.
to see how something is implemented. And if I don't give you a way of knowing externally it is or is not safe to call me with a null pointer, I am forcing you to go read my implementation. There's no ins, ands, or buts about it. And so I say repeatedly that for an industry that talks as much about encapsulation as we do, we suck at it. Because you tell me about encapsulation, I say, show me your code, where are your contracts? And if you don't show me contracts, I feel like slapping you because you're definitely not encapsulated.
There's no other way to do encapsulation? Or is that,
No.
that is really just the
No,
way?
it's essentially it. And so the idea is syntax and semantics are key words. Look, your compiler is a ruthless master of language syntax. Syntax is about structure, semantics is about meaning. And we could get into a big discussion of examples of syntax or semantics in natural language, syntax in natural languages, et cetera, et cetera. Not time for that right now. But as I said, your compiler, it's a ruthless master of language syntax. You write code that violates in the slightest way some syntax rule in the language, and it basically throws up its arms. I can't compile your code. So you're forced by the compiler to pay exquisite attention to the syntax of the code. Okay? Semantics, what does the code mean? What does it actually do? Is a completely different story. And the compiler says semantically, you must have meant what you said, and so I'll just do what you
Very
told
literal.
me to do.
Right.
Exactly. I hate the term bug for a number of reasons, so you'll notice that I tend to not use the word bug. I use the word defect. It's a lot more immediate. It's a lot more honest. Look, my code has a bug. No. It's defective. It's broken. It needs to be fixed. But what most people will call a bug and what I will call a defect is, in fact, nothing more and nothing less than a semantic inconsistency.
Because most of the syntactical stuff is caught by...
The syntactical stuff
By
is
compilers.
already taken care of by the compiler.
Right. Gotcha.
But the compiler is of no help with the semantic stuff. And a clear example of semantic stuff, is it okay to call this function with a null pointer? That is semantic, that's behavior, that's meaning. And so when you look at what's known as the signature of the function, look, here's the function's name, here's the parameters, here's what the types of the parameters are, and if the function returns something, what is the type of the return? That signature, the name, the types of the inputs, and the type of the output, that is known as the signature of the function. That signature of the function is purely a syntactic description of the interface, and so long as some developer writes a line of code to call the function that matches syntactically, the compiler's perfectly happy, the linker's perfectly happy.
You know, it could be a semantic error that gets passed through and it never doesn't pay
Like
attention to it.
null pointer is a really simple example.
Exactly. Okay.
And so in order for me, as the writer of some function, to not force you to look at my code to figure out what the behavior of the code is, I have to give you a semantic specification of the code. What is the semantic of the code? And that's what the contract does. The contract is a semantic description of the interface that sits right alongside of the syntactic description, which is the signature. And so if I've told you what the syntax of the interface is, and if I've told you what the semantic of the interface is, do not call me with the second parameter being null. And when you call me with a second parameter that is not null, here is what I will do on your behalf with the thing referenced by that not null pointer, that it's a behavioral specification, an external behavioral specification of what the code does. Meaning you can write your code to that interface You're not forced to write through the interface by going in and reading the lines of code in my implementation of the function. Look, you have enough complexity to deal with inside of your own function. The last thing I should do is be requiring you to go see
right.
how my function works so you can figure out how to use your function to use my function. And that really becomes the whole point here, is that you have to get beyond syntax. Syntax has been drilled into the developer since day one. Probably the first code you wrote, even if it was hello world. It didn't compile the first time because of a syntax error of some sort.
Right.
But just because you've beat out all those syntax errors, just because your code compiles, obviously it's not necessarily correct. Now you call it debugging. I find it rooting out all those pesky semantic inconsistencies.
Right.
And until we start paying more attention to the semantic of the code, then we're going to be stuck in this loop of not understanding why this code has defects in it. I mean, I was just writing some code a couple of nights ago, and it happened to be assembly level code. And the code wasn't working, and I went back and looked at the code that was supposed to implement this little machine language function. And then I glanced up at what I stated its contract was, and guess what? The violation. If this is what the function's contract is, this assembly code does not implement that contract. So no wonder the code that was using this function wasn't behaving correctly. And so, I need to pay attention to my own contracts. Here is the contract, here is the code that satisfies that contract. Oh, okay, and then instantly the code started working.
So you actually had a defect. I didn't think you had, I didn't think you had defects anymore.
Oh, yes. Oh, yes. Not as many as the average person.
Yeah, that's good.
Am I smarter than the average bear? Maybe. Well, I don't know. No, I just use design by contracts, and that helps me avoid a whole class of defects that a bunch of people who don't pay attention to contracts have to wrestle with.
So this was a topic that came up in the class. That are you surprised at the response that the class had to this particular issue, or a lot of people didn't really did people know about this a fair amount, or was this kind of somewhat surprising to them that this should have been something they were taking care of?
Well, I think that my impression, based on the number of light bulbs that you can see going off in people's head, is that no, people don't understand this kind of stuff. You read the programming language reference manual, you read the books on how to program the language, and they just drill syntax into you. Right. The syntax of a for loop is this. The syntax of that is that. The syntax. And they might kind of hint at semantic, but they're not really very precise about it. And it's actually quite interesting in some languages, C in particular, is that the language standard is in fact a syntactical standard, and that the people who write C compilers are free to interpret certain syntactical structures in different semantic ways. And so you write your code in a way that complies with the defined C compiler syntax, and you run your code through compiler A and it works just fine, and you run the same code through compiler B and it doesn't work because the semantic that they've attached to that syntactic structure is in fact different in a way that causes your code to behave different enough in a way that causes it to break.
Interesting. So this has been around for a long time. Is there any place where you wouldn't use design for contract? Is there any place where it doesn't play? Like
I cannot think of
distributed
one.
systems, distributed computing, perhaps.
No, and in fact, I would argue that in the distributed computing arena, it becomes even more at least as important. It's hugely important everywhere. And so I do want to drop in a little thing here that when you look at things like SOAP and REST and the distributed technologies,
right,
that they do use a term called contract, but I need to point out that their use of the term contract is actually different than this use of the term contract.
Okay, well, maybe that's where I'm being confused. Okay.
Yeah. And at least what I have seen on their use of the term contract, it is still a syntactic description of the interface. It is not a semantic description. At this position in the REST post, you would put in an integer, and in this position you would put in a string and da-da-da. But for example, again, that's syntactic. It doesn't tell me that the string can be empty. It doesn't tell me that the integer could be less than 0. Those are semantic things that are beyond what they're talking about, which really are what make the difference here. A common complaint with projects, the larger the project, is distributed development. I mean, the teams are distributed. You got a team over here in Europe that's doing this part of the system. You got a team over there in some part of North America that's doing some other part. And our code and your code are supposed to interface with each other. And so, of course, we have to agree on the interface. So we'll define the interface, we'll specify the interface. Again, the problem is that interface specification is essentially syntactic. Here's the name of a function, here are the parameters of the function, here's the type of the return value, and maybe an informal description of semantic. Informal, the name hints at the semantic, but can that middle parameter be null or not? And they didn't tell you that. And so the point is that we write our code to the published syntax of this interface and our interpretation of the semantic, and the other team is writing their code to the same published syntax but their interpretation of the semantic. Now, our code compiles, their code compiles, and the code links because the linker only cares about the syntax.
Right.
So now we start running this thing and boom, null pointer exception, and people are starting to point fingers. Hey, your code is broken. No, you don't understand.
No, it's yours.
Our code is perfect. Your code is broken. No, you
Never
don't
happens.
understand.
Never happens.
Yeah. And it's all because the syntax was agreed on, but there were local differing interpretations of semantic. Why shouldn't I be able to call you with the second parameter being null? Well, it's stupid to call me with the second parameter null, but we didn't get an agreement on whether the second parameter could be null or it could not be null, and so everybody's pointing fingers. And so the get well plan here is, especially in distributed development environments where we're dealing with microservice interfaces, et cetera, is that semantic description of the interface is absolutely critical. So then, in addition to matching the syntax, which the compiler and the linker are mostly going to take care of already anyway, that we've agreed on the semantic. And so if things are not working, then it's clear your code isn't honoring the published semantic. Our code is or is not honoring the published semantic. It becomes really obvious whose code is broken because we agreed on the semantic.
Right.
And so things fit together and they work.
Well, that's a great way to close, I think, right? That's a
Sounds
good summary. I like that. You can now drink your beer.
What makes
If
you think
haven't
I
already
haven't been drinking all
already.
along? I notice your glass is almost
I
empty.
am empty. It's time to fill. So thank you, Steve, for that discussion and for your insights into the patterns and these fundamental design principles relationship that you brought up in the class. It's all really good information, and we appreciate you sharing that knowledge.
Thank you, Mark, and looking forward to the next brew day.
Yeah, well, I'm looking forward to you coming back another time. There's lots of information I think that you can share with us, and you've alluded to some of that as well. We'd like to maybe have you come back and talk about your new book in some level of detail, but I got to read it. I got to read it first so I can spin up the speed on it. So.
Good luck with 1,100 and some odd
That's
pages.
right. Well, I'm gonna. It'll take a while, but I'll get through it. So anyway, I think that's going to do it for us today. Be sure to tune in next time for another edition of Inspect and Adapt, the Construx podcast. Until then, this has been Mark Griffin as your host. Cody Madison has been our sound engineer, and Devin Musgrave is our producer. Have a great next sprint. If you enjoyed this episode, feel free to give us a positive rating on Apple Podcasts, Spotify, Stitcher, or wherever you found us. If you have comments or would like to talk to one of our practitioners, or you have ideas for a future podcast, reach out via email using comments@construx.com. Again, that's comments@construx.com. We'd love to hear from you.